Good morning. I am Dr.S.J.Mohan, Professor of Civil Engineering, Bharat Institute of Education and Research, Higher Education and Research, Chennai. Today, the lecture on which I am going to cover is structures on expansive soils. Under this, a specific topic what I am going to cover is design of footings. What is a footing? A footing is a foundation. What is a foundation? Foundation is that part of the structure which will generally be located below the ground level or the water level as the case may be, which will transfer all the loads onto the underlying soil at a tolerable stress level. The tolerable stress level may be a net safe bearing capacity or ultimate bearing capacity by factor of safety or safe bearing capacity and so on and so forth. So we are talking about the design of footing, and footing we call it as the foundation. The basic thing what we have to know is start from the bearing capacity of the soil. For example, the first and foremost footing on which what we are going to start is isolated footing. For isolated footing, the bearing capacity is given by Q is equal to C prime NC plus gamma DF NQ plus 0.5 gamma B N gamma, which is called Tersaghi bearing capacity equation. So using this equation, the bearing capacity of the soil can be very easily calculated if you know the cohesion as well as the angle of internal friction phi value. Depending upon the phi value, the NC, NQ, N gamma can be taken from the graph and substituted accordingly to get the bearing capacity of the soil. Because this bearing capacity equation is valid for infinitely continuous footing, when it wants to be applied for a discrete footing like maybe a square footing, circular footing, or a rectangular footing, some empirical modifications are done over and above this formula. For example, square footing, the Q ultimate is equal to 1.2 times C prime NC gamma DF NQ zero point 0.4 gamma BN gamma. Similarly, for circular footing, you have a formula, and for rectangular formula, both B and L, that is breadth and length of the footings, are accounted for the bearing capacity equations. For example, if you take a circular foundation of 2.4 meter diameter and depth is 1 meter, and gamma if you take 19 kilonewton per meter cube, you get the ultimate bearing capacity of the equation is 426.9 kilonewtons. So you have to substitute phi is equal to 15 degrees, NC is 10, NQ equal to 1.8, N gamma equal to 1. Straight substitution in the formula will yield the value of the ultimate bearing capacity of the soil. If you take the isolated footing, there could be a possibility of the failure because of the local phenomena happening in the soil. For example, the general shear failure, which is because of the movement of the failure of the shear zone in the soil, is accommodated by the called Tersaghi bearing capacity equation. If it is a local shear failure, maybe if the settlement is very sudden or maybe unequal, then you have to need for modifications in the constants. Similarly, there may be a punching shear which can happen to the foundation. It's because of the poor and granular soils or a very small uh, grain soils. You get such type of the puncturing of the soil. Then you get the punching shear of the soil capacity. Again, gamma, D, and gamma, all those things are changed to get the ultimate bearing capacity of the equation. For example, if you take the ultimate bearing capacity of the square footing of size 1.2 meter, if the depth of the footing is 1 meter, then take phi is equal to 25 degrees, gamma equal to 15, and C is equal to 15. Then for square footing, you know the formula is a modified formula 1.2 Instead of C, you get C prime because the square footing can always happen with a local shear failure, unlike a continuous footing which can have a general shear failure. So gamma DFNQ and gamma BN gamma, all those things are substituted in this formula. When phi is equal to 25 degrees, you get NC equal to N prime and NQ equal to NQ prime, N gamma equal to N gamma. From the tables, you get NC prime is 17, 5.7 and 3.2 respectively. The straight line substitution of all those values in the formula of Q ultimate, which will yield a value of 436.25 kilonewton, which is the ultimate bearing capacity of the soil. For example, you take a square footing of 1.2 meter side and located at the depth of 1.5 meter. The properties of the foundation soil are gamma 18 C 30 and Q equal to 20 degrees, NC 11.8, NQ equal to 3.9, N gamma equal to 1.7. Then find the safe load. Previously, we were not applying in this problem factor of safety factors. Now, the safe load is being asked in this problem specifically to understand the application of the factor of safety over and above the ultimate bearing capacity of the soil. For square footing, obviously the formula is QE is equal to 1.2 C prime NC gamma DNQ CQ N.4 gamma BN gamma, where QU is equal to, if you straightway substitute, you get a value of 544.788 kilonewton, which is not the solution for this problem, because the solution being asked on the safe bearing capacity. What you obtained from the called Tersky bearing capacity equation is your ultimate bearing capacity. So you apply a factor of safety of 2.5 over and above the ultimate bearing capacity to get a value of 217.95 kilonewton, which is your safe bearing capacity of the soil. For example, if you go for a circular footing again, you can substitute all those things. Previously, per formula, we get 554.04. You apply a factor of safety of 2.4, you get a value of 221.616. As it is a continuation of the previous problem, so we are not wasting on the time of again repeating the same equations and same values now. So what will be the gross and net safe bearing capacity pressure of the sand having phi is equal to 36 degrees and effective unit weight is 18 kilonewton per meter cube for 1 meter wide strip footings. Strip footing, you may be knowing it is not an isolated footing, it is a continuous footing. So you can embark on the real value of the called Tersky bearing capacity equation. For sand, C is equal to cohesion equal to 0 and NC is equal to 0. Whatever value of the NC you get, because C value is equal to 0, the NC value you can take it as 0. So that term vanishes there. So ultimately, QU is equal to gamma DFNQ plus 0.5 gamma DN gamma. If you straight away substitute, you get 1233 kilonewton per meter square, because width is not given. The factor of safety for the safe bearing capacity is equal to 3 was given as a factor of safety. You get 411 kilonewton per meter square. The net safe bearing capacity is a concept where when the foundation is located below the ground level, then the value of the weight of the soil which is above the ground level on which it is already located, it is removed now. To that extent, it can take a higher value. That is the net safe bearing capacity. But ultimately, when there is a backfilling happen, the concept of ultimate bearing capacity, net safe bearing capacity all vanishes. Then you end up with only the gross bearing capacity, safe bearing capacity. So the net safe bearing capacity is removal of the overburden 1233 minus 18 into 1, which is equal to 1215 by 3, which is 405 kilonewton per meter square, which is slightly less than 411. So gross safe bearing capacity is equal to 1215 by 3 plus 18 into 1. You get 423 kilonewton per meter square, slightly more than 411. That is because the net safe bearing capacity is taken and it is backfill is accounted. So you get slightly more bearing capacity for the soil. These are all the small concepts what is being applied in the foundation engineering. We're coming to the RCC footing, the isolated footing. The water table above the base, the fluctuation of the water table is also influencing the design of the footings. So one small aspect we will cover here before we go to the RCC footing designs. So when there is a water table fluctuations, obviously the self weight of the soil will be influenced by the buoyant weight of the water. So gamma become gamma minus 1, which is the buoyant weight of the soil or the density of the water, because it is being submerged, then the flotation law will come. So the gamma become gamma minus 1, you get the reduced weight of the soil. If you apply that and then find out the value to the part where the submerged soil is there, then you get the ultimate bearing capacity of the soil. So if you apply it, you can deduce the formula QU equal to C prime NC gamma D NQ plus 0.5 B, gamma prime plus B by B. One B is the water table fluctuations, another B is the width of the foundation, gamma minus gamma prime into NQ, where gamma prime is the unit weight of the soil, submerged unit weight of the soil. If B is greater than B, no effect of the water table, because the water table, when it is lower than the depth of the foundation, the water fluctuations doesn't matter for the foundation, so you need not account for it. So IS code method says 6403-1971, or the latest code, you can refer it. It code gives the net ultimate bearing capacity based on the basic equation. Is another soil mechanics expert, just like called Bce078 of Tom Wilson. Think people, great authors like that. So his prediction is Q ultimate is equal to CNC SC plus Q into NQ minus 1 SQ DQ IQ plus 0.5 B gamma N gamma and relevant DI and gamma. These constants are already given in the code of practice to take up the values and substitute to get the value of the ultimate bearing capacities. There are some experimental methods are also there, the standard penetration test, plate load test. Then standard penetration test will give the number of the blows, how much it can resist. Then from that you evaluate the bearing capacity of the soil. For example, a rectangular footing of 2 by 3 meter rests on the soil and base width is 1.5 and below the ground surface. Calculate the safe bearing capacity using a factor of safety of 3. Net ultimate bearing capacity, soil has the following parameters: gamma, C, phi, IS code method. And the general shear failure, if you assume the local shear failure is not there, you take the formula of IS code of practice, then you take the code of practice, whatever the constants given in the IS code, NC equal to 30.14, NQ is 18.4, N gamma 2, 22.4, then shape factor for rectangular footing, you can account for it, and B equal to 2 meter, L equal to 3 meters. Then depth factor, you can account for it. Then you can calculate DC, DQ, and IC, IQ based on the depth factors. Then Q is equal to gamma D, then C, NC, SC, DC, IC, plus all those values are there. Gamma DF NQ minus 1, you can have that value. Then half B gamma N gamma S gamma D gamma, all those values are there. It is given in substitutions. All those numbers are also presented here. So QU ultimate is equal to total, you get 1365.56 kilonewton per meter square. Since it is a continuous footing, the length of the footing is not given. So similar to that previous problem, net bearing capacity equal to minus gamma D, you get a value of 1338. The net safe bearing capacity divided by factor of safety, you get 446.189 because factor of safety is 3. The gross safe bearing capacity is add onto the surcharge of the soil 446.187 plus 18 into 1.5, you get 473.189 kilonewton per meter square is the ultimate gross bearing capacity of the soil. So design a square reinforced concrete footing. Following the data, the column load is 700 kilonewton, allowable soil pressure is 200 kilonewton, say the size of the column is 0.4 by 0.4 meter. We are entering into the RCC structure now. We are just briefly touch upon that and then go, because even though we talk only on the foundation related to soil, but we should know when when the superstructure sets on, when the foundation set on the concrete, how when the foundation sets on the soil, how the RCC structure behave with respect to soil is also very important to understand that. To understand that, we take a RCC footing and then design and what are the implications because of the soil, we'll try to explain also here. Column load is 700 kilonewton. So soil pressure is 200 kilonewton per meter square. Area is known now. Because a square foundation, 3.5 meter square is area required. So square foundation, you take a root of that. You get 1.87. So 1.9 meters. So your footing is 1.9 meter by 1.9 meters. So the pressure at the base, the column size is 0.4 by 0.4, that is small b. The capital B is the size of the footing. So the net upward pressure as per the drawing, B minus B by 2, because B minus B is the total width minus column. On one side, it is B minus B by 2. So the maximum bending moment is equal to Q naught is the upward pressure, B is the length on one side, and the projected area is B minus B by 2 into its lever arm is B minus B by 2, half of that. That is the CG of the load, and that is your bending moment at the base for the footing. The maximum shear will be after the 45 degrees of the dispersion of the concentrated load. So the shear will be B minus B by 2 minus D, where D is the depth of the footing. So if you take the 45-degree distribution, the shear will act only after the depth of D from the face of the column. So the shear force is Q naught B, and the B is the length of the footing. B minus B by 2 is weight, minus D is for the distribution of the concentrated load at 45 degrees. So you get that formula, the depth of the footing is obtained from the punching shear value. The critical section for the punching shear is taken at a distance of D by 2 from the face of the column. The of the distribution depth, you call it as the punching shear, or D is the full depth of distribution. Off of that is the center of your footing depth, where that shear you have to work out, that is D by 2. So sigma SP is the safe punching shear stress, then Q naught B square minus B by 2, it should be equal to D naught into 4 times V plus D into sigma safe bearing capacity. Assuming the punching shear strength equal to 1000 kilonewton per meter square, you assume a value. Normally in the design problems, you assume a value and then check for it. So you assume that value, now you equate it, the safe bearing capacity to the punching shear, you get a quadratic equation in terms of the depth of the foundation. You solve for D, it is equal to minus B plus or minus our old B square minus 4AC by 2A. You substitute for all those values, you get a value of minus 0.66 and 0.242 meters. Obviously, a negative value, the depth of the foundation cannot have a negative value, so the positive value of 0.242 meters is taken as the depth of the foundation. The moment the depth is known, then it is equal to 320 including the cover of 80 millimeters. With a cover of 78 millimeters, you get the maximum depth equal to 320 millimeters. So maximum bending moment, you substitute in that old formula Q naught B into B minus B by 2 into 194 into 1.9, 1.9.4 whole squared by 8. You get the bending moment is 103.67 kilonewton meters. And maximum diagonal shear, again you can substitute the same formula QB B minus D by 2 minus D, which is the shear is after away D from the face of the column, you get a value of 158.498 kilonewtons. So the bond force, you can equate it to F2 is equal to Q naught B, B minus 2 by 2, you get a value of 276. On punching shear, you can work out 620 by 621, you get nearly 1,000 value, you will meet it. So you will get check for the bearing capacity of 1,000, you get a value of 999 in the previous slides. That is as far as the isolated footing is concerned. Now we will move on to continuous footings. Find the planned dimensions of the rectangular combined footing for two columns of size 450 millimeters by 450 millimeters and 500 by 500 carrying a load of 50 kilonewton, 750 kilonewton respectively. The columns are spaced at 4 meters center to center. The allowable bearing capacity of the soil is 150 kilonewton per meter square. First of all, the continuous footing way it comes is when there are closely spaced columns are there, when the footing is being joined, when the footing is being designed, if the size of the one footing fall on the other side, other footing, then you combine both the footings. You get a continuous footing or a combined footing. So as in this case, you take it as a total load, then you get a combined dimension footing. Only thing is you see that the CG of the loads passes through CG of the upward pressure of the soil. To avoid any eccentricities or variation of the stress level at the bottom. If the CG matches, then the uniform stress distribution is assured from the soil end. So that is essentially needed because otherwise you have to solve for the variation of the variational stresses, triangular variation of the stresses, and stress concentration point should be taken into account. So you can find out the CG of the column, which is 2.4 meters. Then area required, total load by SBC, you get 8.33 meters. You have the spread of the column is 4 meters. Then you know the value, meter square is known, width is known. Then the length of between the column is known. You have a margin on either side, 450 one side and 1250 on the other side. Select the length and width of the footing such that the center of the footing and the resultant of the column loads coincide of the length that is equal to the minimum of the CG length of the column plus column width by 2 plus a margin if needed. So that is the formula normally. It's a common formula normally we follow. The CG of the loading should match with the CG of the soil, upward pressure. You get a length, then you get a width. Because the length is fixed now based on the CG, if you divide by that, then you get the width of the footing. So your soil will be 1.46 meters, then say 1.5 meters, then actual pressure is equal to 1250 by 5.7 into 1.5, you get, which is 146 less than 150. So the load which is applied on the soil is much less than, not much less than, very nearly economical way of loading it. So which is very nearly equal to 150 safe bearing capacity. So the size what you have fixed up may be 100% economical solutions. Then you can do a static check. So RB the load into 4.4 into 219 into 0.45, you get the RB value. then 3000 kilonewton, you get 750 kilonewton. Then Ra is equal to 500 kilonewton. Maximum shear for the foundation is 476 kilonewton and maximum bending moment is 345 kilonewton meters. So it is 1.83 meter from column. So you can solve the problem by theory of simple bending. There are two values of upward loads and there is an uniformly distributed load. So you solve for the beam problem and get the maximum bending moment and the shear. Similarly, when the column loads are very heavy and sizes are very heavy when compared to the other column, you recover a larger area of the spread of the area and for the larger column and a smaller area of spread of the foundation for smaller column. Then when we have a combined footing of this, you end up with a trapezoidal continuous footing. Here also you see that the CG values of Q1, Q2 and then CG value of the upward pressure of the soil matches. Then you get the condition L by 3 which is less than L by 3 which is called as the middle third rule. Middle third rule is if the CG passes through in between the middle third values, then the tension will not happen at any one end of the column. The full footing will be exposed to the compression, but variation of the stresses may be there, but zero value or a tension value will not appear in the foundation end. So area of the trapezium you get B1 plus B2 by 2 into L equal to area. And CG of a trapezium you know 2/3 of that, L by 3 of 2 times B by B plus 2. Solving you get B1 and solve that problem B1 to get substitute in that and Q1 Q2 to 10 and you get area is equal to 10.5 meters square. So your X bar is equal to 1.71 and X bar is equal to 1.71 plus 0.3 plus 0.35 is 2.21 meters. So your length is equal to 2 times X bar which is equal to 4.42 and length is equal to 4.47. From the original formula you can substitute all those values. So L by 3 equal to 1.57 and L by 2 equal to 235, X bar is 2.21. You get B2 and then equal to 1.85, B1 is equal to 2.65 and that is the size of your footings. Now the average intensity of the pressure you can work out from the formula. So you know the area of the trapezium, then you know the load, you get a value of 198.58 less than 200 kilonewton per meter square, which is the safe bearing capacity of the soil. So the load intensity, P pressure at the column B1 is heavier and pressure B2 is lighter. That you can get it. So it is 526.237 and it is 367.373. So again you draw the theory of simple bending equation. There is an upward load of the column. Then the intensity of the pressure is 526 to 367. It varies because the width of the footing is varying. So you get the intensity of the loading also varies, which is a trapezoidal loading. You solve the theory of simple bending, then you get the statics from the static principle, you get the shear, you get the bending moment because of it's a determinate structure. From the basic principles, you get the shear if phi 0, bending moment maximum is 1059 kilonewton meters and shear force maximum is 941 kilonewton on the heavier side of the column. Now, the location of maximum bending moment, you can solve it by means of the mathematical equations. You arrive at 1059 kilonewton meter. And basically, because it is a second degree parabola, and you know its CG where it acts, it is 2/3 of the rectangle, you take that value and then get those values of maximum bending moment in the continuous footings. Of course, the detailed workings are already given in the working sheets of my presentations. So you get Q naught, you get a D, the depth of the foundation as you get 242 Newton per millimeter square is the depth of the foundation. you solve for the quadratic equation and end up with the depth of the foundation. Then location of the bending moment you found out. Then for that bending moment, and then you design for the RCC footing, what is the steel area you may require it. Then we'll go to the mat foundation or the raft foundation. The raft foundation is a continuous foundation on lengthwise as well as the widthwise. The continuous foundation is a continuous foundation on only one direction, but mat foundation is a spread footing which is on either side, it is continuous. The mat foundation will look like that. There is a lot of columns, all columns are combined with a stiff mat or a rigid mat. Suppose the mat depth is not sufficient, you will have the columns and you can have the wall ribs, what you call it as the wall ribs, are also there, and these wall ribs will transfer the load to the mat, and these wall loads will receive the column loads and distribute it. So the ribs are also provided in mat with the ribs and mat without ribs. These are all two types of the mat foundation. Some guidelines are here to discuss about or to design about the mat foundation. For example, the following equations are given. The very familiar equation is the Skempton equation, where the bearing capacity is equal to 5 times 1.2 d by b. One is the one dimension, another is another dimension, d is the depth of the raft, b is the width of the raft, l is the length of the raft. You get 1 plus 0.2 into b by l into c. C may be coefficient value. Subject and then subject in the condition of d by b should be less than 2.5, and the factor 5 into 1 plus 0.2 by d by d does not exceed 7.5. So the Tersaghi equation also closely follow that, but most of the time Skempton equations are being followed. A factor of safety of 3 should be used when you use the safe bearing capacity. Arrive at the safe bearing capacity. A building is to be supported on RCC raft foundation of dimension is given, that is length is 18 meter, width is 12 meters. The subsoil clay is an average unconfined compressive strength of 15 kilonewton per meter square. So UCC value is given. You have to work out the C value. The pressure on the soil due to the weight of the building and the loads will carry is expected is 130 kilonewton per meter square at the base of the raft. If the unit weight of the excavated soil is 18 kilonewton per meter square, determine the depth at which the bottom of the raft should be placed to provide the factor of safety of 3. The solution is the soil is phi is equal to 0 because cohesion is given, very high cohesion value of 15 is given, UCC value 15 is given, so its C values of that is 7.5. Now Q enough is equal to 5 into 1.2 by d by b into 1 plus 0.2 b by d, and d by b is less than 2.5. You substitute all those values there, you get, but d is not known, b is known, l is known. Since the building will have the basement, the excavated soil is not going to be replaced. Hence, it is possible to allow an increase of gamma d in the safe loading intensity. So gamma df is equal to gamma d, equating this value, Qs is an actual load intensity of 130 kilonewton. We get a value of d equal to 6.35, and that's how the mat foundations are being designed. You have a code of practice is available. So as per that, raft foundation is 65 to 100 millimeters, and raft foundation on sand is 40 to 65 millimeters. So minimum requirements are given in the code. The other depth of the foundation you have to evaluate based on any formula like a Skempton formula. We go to the next type of foundation, what you call it as an under-reamed pile foundation. The pile foundations are very deep foundations. Under-reamed piles are special type of foundations under pile foundation categories. An under-reamed piles is also a pile which is being bored into the soil with a bulb. The bulb is provided at the bottom to get the higher uplift capacity of the piles. There may be a one bulb, or sometimes you can have two bulbs also there. The design of under-reamed piles are very easy if you go in for the code of practices. Anyway, we will going to cover that. Code of practice for design and construction of the pile foundation, part 3, under-reamed pile, it is available, and that we'll straight away use it to design it. The under-reamed piles, you can say one few words. When ground consists of expansive soils, for example, black cotton soil, the bulb of the under-reamed pile provides an anchorage against uplift. In case of filled up, otherwise soil also overlying soil, the firm strata enlargement base will help you. In loose to medium previous or silty strata, then the bearing capacity of the piles can be increased because of the bulb. Under-reamed piles may also be used under the situations where the vibrations and noise caused during construction piles to be avoided. The provision of the bulb is of special advantages in under-reamed piles, which resist the uplift capacity. So the IS gives the what is the steel reinforcement you should use, what is the stresses allowed in steel, and under-reamed piles when you use it, what are the types of the pile, what are the machines you should use it, what is the cement you should use it, what is the concrete you should use it, IS 456, IS 455, all those codes are taken into account in the code of practice of under-reamed piles, and all those things are covered automatically. So the design considerations in the deep deposits of the expansive soil, the maximum length of the piles, irrespective of any other consideration, shall be 3.5 meters below the ground level. The expansive soils, non-expansive soil, good bearing rock piles of smaller length can also be provided. In recent filled up grounds or other strata, the poor bearing capacities are there, but normally the diameter of the bulb should be 2 to 3 times the size of the diameter of the pile. You cannot have a small bulb like this shown in the figure, you call it as an under-reamed pile. It should be 2 to 3 times the diameter of the piles. So these under-reamed piles are useless piles. So under-ream should be as per followed by the code of the practice. So design consideration, as I said earlier, so the topmost bulb should be at 2 times the bulb diameter. All those things are provided in the code of practice. So we have to straight away follow the code of practice to design the pile foundation. The minimum diameter of the stem should be 30 centimeters. The minimum diameter of the stem and then borehole leading mud should be 25 centimeters. So under-reamed piles with more than 2 bulbs are not advisable generally. So you cannot have a number of the under-reamed piles, maybe 10 pore will be increasing. It is not so. Because the moment soil fails because of the uplift, the one bulb will be coming out with an uplift capacity of the soil, and other bulb will be a redundant presence at the depth. So 1 or 2 bulbs will be sufficient to get the full functioning to the satisfaction of the under-reamed piles. The load carrying capacity of the under-reamed piles depend mainly on the pile dimensions. So axial load depending upon the nature of the soil, pile geometry, things like that. Piles as a structural member, you can combine some of the under-reamed piles and then develop a structure on that. You can use that as a column and go for the multi-story buildings. The pile cross-section should be checked for the combined effect of vertical loads and compressive uplift and or lateral loads and then moments. So you can design for the moments, you can design for the shear just like a structural member. So under-reamed piles will look like this, where you can have the reinforcement in the piles. You have to scoop out the soil, then you insert this. You have to scoop out the soil at the bottom with a special fixtures, which I am going to cover it up now. And then you can put the reinforcements and then you concrete it so that the bulb formation is also ensured 100%. So this is an equipment used for the under-reamed piles, where you have a lever. If you press that lever, after going into the soil, it opens out. if you give a torque, then the area at the bottom will be scooped out. Then you get the enlarged diameter at the bottom. Then you can scoop out those soils and leaving those soils there, and that enlarged bulb will be filled with a concrete. You call it as the underreames. This is an actual photograph. A screw pile can also be used as an underreamed piles. This is the lever. When it opens out, it can scoop out more wider soil than the ordinary screw piles or ordinary boring equipment. So sometimes you may require a triangular scooping. A special scooping materials are also used for the underreamed piles, and they are called belling buckets. Underreamed belling buckets are also available, and lot of high torque application equipments are also available. So that's an it's a very high torque equipment. You can apply it can go into the weathered rock for scooping out and then making an underreamed piles. So equipment used for the underreamed piles sometimes will be very heavy duty machineries. And you may be thinking you put a pile and then you are very happy with the pile foundation because its capacity is very high, and not necessarily, and sometimes pile gets damaged during the course of time, not only in the water, and when it exists in the soil also it gets deteriorated. So piles damages should also be warned and then taken care. Thank you for listening. Thanks for joining with me. You can please join for the next lecture also in the few days to come. Thank you. Thanks for one and all.